now let's start talking about the use of graph technology in network and IT operational products. So the way this webinar is playing itself out, or the way it fits in our series of events now on network and IT operations, is this one is really intended for vendors who serve the space. And so, as you're building a product that serves the IT operation space or the telco space, this is an event for you. So, why is graph particularly important? And really, the way we look at the world is, the connections in the data are really what's driving the most interest and the most richness about the data itself. And then it's also the ability to take those connections and do something with them that improves either your customer experience or improves the information that you're able to provide your customers. Now let's take these two kind of phrases and really look at them from another kind of viewpoint. When we look at connections and data, what we see here is that's often a function of time and how your data evolves and how it adjusts and changes over time, and how the connections in that data and that information changes over time. In the context of telco here, let's look at it from how perhaps a network topology changes, or a customer base changes, or the different sets of call features and capabilities that a telecommunications company might provide changes over time. And then let's juxtapose that with the ability to leverage those connections. And here we're looking at, really, this is how are you actually going to take advantage of the fact that connections are changing as a function of time? What technology are you really going to use and choose here to take advantage of that interconnectedness? And of course, we like the idea here of a property graph to actually help take care of that exercise. Property graphs, of course, have nodes, which are, if you're using graph theory, nodes are called vertexes. We like nodes. It's a little bit more more natural to think of a graph this way. And then your edges in academia, we call those relationships. Again, a little bit better context and a little bit more personal and understandable by everyone out there. So we talk nodes and relationships, and then we talk properties and labels and whatnot that are attributes of either nodes or relationships as we go along. So these nodes and relationships and how they end up when you look at your data connections from a generalized kind of understanding, it really can expand into a massive amount of nodes and relationships and connections throughout your data. So imagine, I think one of the reasons why we like this particular slide in this context is it really does show the complexity of what we're trying to and the interconnectedness of a large telco network or of the products that you're trying to build for them. So let's look at a couple of, what's the origins of this idea of a graph, or of how disruptive this kind of graph idea can be. And we'll look at it from the context of what everybody's familiar with, the web. And so prior to looking at the world from a standpoint of interconnectedness, we had search engines like AltaVista and Lycos, and they were really just indexed documents. And they would look at the documents themselves, those series of pages, and deliver back whatever search results you were seeking. Now, when Google came along, they had the PageRank algorithm, and what was interesting about PageRank was that it took into account the connectedness amongst those different websites and those different web documents. So PageRank is really the first introduction of a graph idea on the web. Our next kind of a very quick use case is, how about if I'm looking for a job? I'm either searching Monster, I'm searching Craigslist for particular keywords and attributes about a job. But then when LinkedIn came along and LinkedIn started to look at, leveraging your network of associates and prior contacts as the means to get your next role, LinkedIn really is dominating that particular space right now. And even in the financial space, when you had banks dealing with transactions and ATMs delivering you your cash, all very handy, but then PayPal rolls along and starts creating a payment network of users and means to trade money over the internet via the PayPal network. Again, leveraging the relationships amongst people and transferring different funds to different organizations or individuals. So those are all kind of examples of the interconnectedness of the world we're living in right now. And so what I want to do is, and this is a sharp-looking picture of myself, but what I want to now transition into is let's talk a little bit about building a product that takes advantage of these relationships in the context of building out capabilities for a telecommunications organization. Perhaps that's the target market that you're going after. And so as a PM, the kind of activities that you're looking for and we hope to answer today in our webinar are things like, can we indeed improve your time to market? Can we indeed develop a long-standing relationship with you as a vendor? And are we actually going to add so much significant value that it makes it worthwhile to incorporate a Neo4j-based graph in your application? Right? And of course, you're going to have other issues. Is it going to scale to a telco network's size and complexity? Is it going to be easy to embed and bring that several x, 10x kind of more value to your product? And have I got anybody else I can refer you to actually validate whatever claim I happen to make today? Now, if you're a developer in an organization, you're going to want to look at things like, how productive can I be in learning and then using this kind of graph technology, this cipher query language that Ryan is going to end up talking about in a second. How well does it integrate with the rest of your environment? Is it invasive, or is it something that simply slides in and is immediately complementary rather than requiring you to rework other items of your environment? And does it scale? Does it support clustering? Does it support high availability, failover? The things that you and your customers really depend on and expect out of an enterprise caliber product. Is it easy to upgrade? Do we follow your upgrade paths? Things like that. Is there enough training for you? And ultimately, can I indeed integrate it and incorporate it into your own skill set? So we'll have Ryan talk quite a bit about those different capabilities. So for those of you that don't know Neo, or we'll give a quick refresher, we are the original and leading native graph database on the market today. And we really believe in the connections in your data as being as important as the data elements that or entities that you may be using and building within your application. So we created the Neo4j database as a way to give you the ability to take advantage of that. And when we talk about native graph database and the way in which you can do that, we typically like to talk about doing things in a real-time transactional nature. So of course, that puts the onus on us to make sure that the environment is indeed fast enough to support real-time capabilities. I lived in the world of analytics prior to joining Neo4j, and one of the ironies of the analytics space is there's a lot of latency involved in either filling a database or querying a database, filling a cube, querying a cube. And those are kind of activities that Neo4j really excels at. So when we talk about latency, we're talking about milliseconds, that kind of responsiveness. And as we get a little bit further into our presentation here, we'll talk even more about that. It's really all about not only providing the richness of those connections, but also providing a very, very fast means to traverse the graph or obtain that information. So very quickly, let's compare and contrast it to some other technologies in the space. So unlike your regular traditional tabular-based models, we connect the data as we store it and insert it into our environment. So we take those data connections, and instead of storing everything in a table of rows and columns, we're storing it as nodes and relationships. And then we use properties or attributes of those nodes and relationships to really enrich and create much more meaning out of each of those data elements. So we write it as we store it, and store it natively as a graph. So when you're thinking about this in terms of what it's like to build a graph database, there's a couple of considerations here. One is we're schema optional, and what that means is if you really want to be operating in a completely unconstrained manner, not have schema drive or dictate the structure of your database, you can build that as a graph. A graph is a really natural way to think about how things are related, how they connect, and how they might evolve. Oftentimes, when we draw things on the whiteboard, we're drawing either hierarchy diagrams or connection diagrams, network diagrams. Those are all easily represented and stored in the native graph database that Neo4j creates. So we like to talk about the way that we connect your whiteboard drawing as a logical entity to the physical model that you actually define and want to store as data, and then ultimately to the linguistic model of querying that data through our Cypher, our query language. All of that is generally the same. The way that you think about it is the way that you draw it, is the way that you store it, and the way that you query it. So all of those exercises are what make Neo4j as a native graph database really very rich and robust as well as fast. So let's talk about one of the core capabilities here is what makes this thing so fast. So we have a feature or a core technology, our IP, is called index-free adjacency. And what this means is that when we're connecting and storing any of the nodes and relationships in the database, we identify what every node connects to and who it's where its relationships lie, and then when we are traversing the graph or looking for who's connected to what we're doing is we're actually chasing the pointers to the next available node. So we're not doing join lookups. We're not doing other externalized references to where nodes happen to live. We store the pointer to where that next node happens to be. And when we're executing our queries, it's very, very fast. And the cool thing about it is every one of those relationship hops that we happen to do has a fixed cost to it, right? A fixed amount of resource or time that it's going to use. So the larger your graph and the more traversals you're making across your graph, the more predictable and linear the cost or the overall amount of time is going to be to execute that query and identify all of the connected nodes, regardless of how many levels deep or how broadly you want to traverse the graph. Index-free adjacency is the capability that does that. That's one of the hallmarks of a native graph database. So where would you use this? And we use it in two particular areas. One is to power applications that are operating at internet scale in real time. So those applications, and then the other way that we use this is powering analytics and BI activities, knowledge graph activities by laying out a graph or a topology that can be used by data scientists, that can be used by analysts and whatnot. So when we're looking at the real-time applications, those are operating and typically serving users. They're typically serving and dealing with transactional data, and then reading additional information in the graph so that the next transaction is benefiting from the connections that we've just traversed. So think of it as real-time recommendation engines are great for graphs. Transaction analysis applications like fraud detection are great for graphs because you want to take and look at what's happening right now, compare it to some elements in the graph, and then inform the next activity that you do upon the graph with that information. So then when we're looking at analytics, the analytics and that are revealed through the connections are really what is quite interesting here. So we feed visualization tools, we feed data science activities, we feed additional analysis. And what's most interesting here and we're finding is that the analytics that are taking place upon a graph are often feeding next generation machine learning and next generation artificial intelligence kinds of applications. So the difference between what we're doing with a graph and other prominent data technologies really breaks down into a couple of key elements here. So if you look at an RDBMS, a turn of the century database, they're really good for handling discrete problems. We often characterize it as handling form-based problems. So you fill out a form that is a transaction that then you have to store and make persistent. RDBMSs are great for that. But where they lack is handling and demonstrating the connected nature of the relationships within the data is very difficult for a relational database. Relationships are basically expressed as joins in the database itself. So if you're trying to express a relationship that has 5 degrees of separation, let's say I am related to my wife who interested in books as a writer, and she reviews different books, and publishes them in Facebook and Instagram. Those activities that I've just described, I have a relationship with my wife who has a relationship with books that she reviews and publishes somewhere. That's 5 hops I just listed out in a sentence. Expressing all of that information in a relational database is very difficult. So, of course, then we have our other favorite NoSQL kinds of capabilities, our big data systems. Build and fill a data lake with all the information that you have. It's your singular central location for all the information, and it allows you to find many needles, or dive deeply into your data lake to find whatever you're looking for. It's great for deep dive kinds of calculations, deep dive kinds of exercises for analytics, for MapReduce applications and activities. But the bummer in your data lake is it still doesn't express relationships very well, and it still doesn't deliver that real-time responsiveness that your transactional applications might need. So here's how we fit into that kind of equation. So basically, when we're looking at the world of take your data from a relational database, those elements that are indeed connected, we'll express them as relationships as we insert them into Neo4j, and then take actually one or more of those different data sources. Oftentimes, this is an age-old problem. They're siloed in different departments or in different locations, different types of data storage. Imagine what it would be like if we were actually to take and connect all of those different data elements. Be really very expressive, and that's where Neo4j often fits in, is an overriding layer that expresses perhaps the relationship between users, their access rights, and their features that they may have available to them on within their telco network, how they're interacting with them, what their location happens to be, where they're traveling, if they're on a cell phone. Those kind of activities are really expressed well inside of a graph. Now, what you'll notice here is that the graph itself is non-invasive in its, it uses the data that is made available to it, but it doesn't impose restrictions on that data, nor does it impose integration restrictions upon that data. It operates as an independent actor and really complements the information that you already happen to have. So finally, we'll start to talk about the adoption of Neo4j and graph technologies. We love this particular prediction from Forrester. 25% of the enterprises, they were saying back in 2014, 25% of enterprises will be using graph databases by 2017. Well, that's right now. So as of today, we're seeing that over 50% of the Global 2000, those are organizations who have revenues of over $1 billion, are using or piloting Neo4j. We know that already. So what do we say, Ryan? Forrester was half right? Additional adoption highlights. In retail, right, we're seeing Neo4j usage in 7 out of the top 10 retailers in the world. In finance, half of the top 25 financial services firms. In software, 8 out of 10 of the top software vendors are using Neo4j right now. Use cases that we're seeing. Real-time recommendations, that we're seeing that at Walmart. Fraud detection. A Fortune 100 bank is doing a wealth of information in the fraud detection activities. Of course, they really don't want me to tell you who they are. Network and IT operations, which is our topic today. Hewlett-Packard is a wonderful example. Their entire network and IT ops are operating in Neo4j. Master data management and regulatory compliance, another great example found at Cisco. Oh, they happen to also operate in the telecommunications space. We have graph-based search and knowledge base, knowledge graphs at Lufthansa. And finally, we have identity and access management happening within UBS. So you can see these kind of use cases. The commonality that I think we see throughout this, except for me, well, yeah, actually in all of them, there's some sort of human connection to the information that we're dealing with across all of these different use cases. Whether it's a buyer, whether it's a thief, whether it's an IT administrator or users, whether it's information management and knowledge workers, both in the MDM and graph-based search, or users themselves in identity and access management. Those are all situations that, and all types of applications that have some kind of human interaction with them. And you know what is really well expressed with the graph is human relationships and interactions. So the future here we're seeing with in the context of network and IT ops kind of goes as the following. And you'll recognize this if you watch any of the earlier events here that we've performed. We like to search for network diagrams. We like to use them as examples of, you know, the way the world models things. Oftentimes is as a network diagram. So here's a great telco network. We've got Wi-Fi, we've got cellular, we've got WiMAX, we've got routers. We've got connections to the internet. We have, oh, even a poor connection there. So something is breaking or we're experiencing an outage. That's really, really well expressed as a Neo4j graph. So mapping these things out as a network topology is very, very natural in the world of graph. So let's look at some of the core kinds of problems that we know that we can address in providing network services to a large user base. And we typically see these often as different layers, you know, a topology itself. We have the core sets of services that the network service vendor is providing. So perhaps you're routing a call, perhaps you're playing a movie, or you're delivering video. Those are the kind of services we're talking about. Then there's, of course, your operational tasks that your administrators are taking on. That's upgrading, that's reconciling issues, those kind of things. There are indeed your key systems that you're using, whether that's SAP, it could be Oracle, it could be other CRM systems, it could be cloud systems, and the like. And then finally, there's your hard assets, your routers, your servers, your networking equipment, your load balancers, etc. All of those are actually interacting with each other. So recognizing all of these cross-domain dependencies across each one of these, from an asset to an application to the activities that IT people are performing to actually core services and features and capabilities that you might indeed be selling to your customer base. Those are the interdependencies that we're trying to display, are really nicely displayed as a graph. So common kind of scenarios here that we might see: vulnerability in the security world, impact analysis. There's, you know, your overall asset management, and how are you going to drive down your technical debt, whether that's, you know, you want to remove aging hardware, you want to upgrade aging systems, those kind of things. There's dynamic SDN configuration and management. So what kind of network services are you indeed providing? There's load and route management. We'll talk more about that in a second. There's multi-channel contact, right? Your customers are often have connections perhaps through their cable system, through their cell phone, and through through their internet connections. So all of those might be in play through multi-channel contact. And then, of course, your help desk. And, you know, if you're selling to or helping assist any of the major telco providers, customers are a finicky bunch, and serving them or providing them degrees of service is often the key differentiator in your own offering. So what are some of those core issues that we happen to have, or when you're looking across all of these types of environments, is indeed that lack of visibility from one layer to the next or one domain to the next. And imagine the exercise of troubleshooting this, right? If there's some kind of service level outage or service level issue that's caused by an administrator needs to know about, that's affecting an application, and then indeed is caused by a particular hard good asset, we need to actually provide that visibility up and down the stack, because without that, right, it's oftentimes difficult to discover what's going on. It's difficult to correlate the issues from one layer or one domain to the next, and it's difficult to deliver that high degree of good customer experience when in fact you can't trace what's going on inside the network. So we like to use what we'll call a network natural approach. And really this is expressing all of this activity as a graph. So if there's a particular issue that a customer is experiencing through a switch that may actually be happening at a router, that's really much more obvious to see in the graph than it is in the layer diagram that we're looking at on the left. So when we're doing this, we're able to actually identify root cause much more quickly. Correlations are really not only intuitive but obvious, and the customer experience can be modeled so that you can be proactive about helping and fixing this long term. So that kind of sets the context for what we're trying to accomplish here. Next, we'll start to talk a little bit. I'm going to bring Ryan in to talk about real-world telco-based scenario. And in the context of what we're going to talk about here, Ryan, is we're going to go through what, a dynamic call routing example? Is that what we're doing?
Actually, first, Jeff, I think we're going to just go through some examples of dependency analysis and root cause analysis, and then we'll talk through the dynamic call routing system.
Okay, cool.
So we're going to, go to the high-level sort of network scenarios here, and I'm going to have to hop out of the presentation and go over to my browser here. So this is the Neo4j sandbox. You can access it at neo4j.com/sandbox, and we can send out a link in the follow-up email to that. But the Neo4j sandbox allows you to browse a number of different use cases for Neo4j, and for each of these use cases, whether it be recommendations or some social network analysis with Twitter, or analysis of some data journalism data sets around Legisgraph or Panama Papers or Trump World, you can launch that sandbox and you get an interactive guide that guides you through that set of data, and the set of data itself. And so we're going to show you our network management network management sandbox, which is available today on the Neo4j sandbox. And if we go here, I've already launched it just by clicking on one of these green launch buttons here. And I can then click on the Neo4j browser, and this is the Neo4j developer interface. This is an interface for developers to look at the data that they have in Neo4j. Here are all our different nodes and all our different relationships and some properties that we're going to get into. You look at the data that you have, and then you can actually run queries on your graphs here. But this guide for network and IT management guides you through some of the use cases, and you can see here what our data looks like as a graph. It's a little complicated here, but basically what we're graphing out is a data center and the network and the machines and the switches and the SAN and some other information about an IT system. And it's all in our database here with these guides that allow you to walk through and see what that data looks like when accessed via Cypher. Now, Cypher is the query language for Neo4j. We call it Cypher out of kind of the original roots of Neo4j with the matrix. But Cipher is a declarative language optimized for graphs. It's very similar to SQL from that perspective. If you can get to learn SQL, you can certainly learn Cipher. And it is optimized for graphs in that it makes it really easy to query the relationships between your data. And that's what graph database is all about, understanding the relationships between data and making those first-class citizens within your database. So here's an example of a very simple Cipher query saying, find me a data center with name is DC1 located in Reykjavik, and where that data center contains a router, and that router routes over an interface and then return that network. And we can see that network returned here. This is our DC1 that we searched for in Iceland, and then we have the various routes of and interfaces from DC1. So that's just a basic overview here of the sandbox and Neo4j's browser, as well as the network and IT data set that we have here. I'd encourage you all to start up a sandbox of your own and walk through these guides step by step, reading information and executing these queries yourself. You don't need to know Cipher in order to go through and click on these queries and then click on the play button here. It's very simple. You can run all of those without truly understanding them, but then you can read them and get to learn about Cipher. So that is the overview of what you can do on your own entirely. And now I'm going to give you a quick demo for a scenario that we have here. And the first scenario is that we are going to be taking part of our network down. And we're taking it down for maintenance. We're going to take down a particular switch in our network. And the idea is that traditionally, as a network admin decides to take down a switch, they're going to notify the sysadmins probably within their organization and tell those sysadmins, hey, we're taking down this switch. They'll probably notify all the sysadmins and not any particular group of them. So the sysadmins will then decide with that email, does it apply to them? Does it apply to their systems? And the sysadmins will then say, okay, some of this applies to my systems. I'm going to notify the app admins. And the app admins are going to look at the system and say, okay, some of this affects some of my users. I'm going to notify my users. And it's this telephone game where there's a huge loss at each step in the way, to the point where eventually you have the CEO calling up and saying they can't access their dashboard at 5 o'clock on Friday, and they're trying to prepare for the board meeting that's on Monday morning. So why can't they access their dashboard? And honestly, they would have been able to access their dashboard if you didn't take that switch down. And ideally, you would have communicated with them that that switch was going to go down. But the telephone game doesn't allow that. So the idea here is you graph out your entire network in Neo4j in the graph, and then you can see, hey, I'm taking this switch down. Let me find, that switch is in a particular rack. Rack holds a set of machines. Those machines run processes. Those processes are instances of an application. So let me find all of the users or groups that depend on this particular switch. And we can see here that for the most part, we have our CRM system is the application that is on a machine in that switch, on a machine in a rack that is supported by that switch. And so we can see here are the different users of our CRM that we might need to notify, and there's a handful of users here, but then there's an entire group, an entire department that depends on the CRM, and that's the sales department. So we can see just the users and that are depending on that switch, or depending on the CRM, and the CRM is depending on the switch. We have 9,715 users that we might want to notify and say, hey, this is a problem. But as you go down here, we can actually dive further into the information and say, oh, we have 9,715 users, but they're spread across some different departments and some different regions. And in particular, we're doing this on 5 o'clock on a Friday afternoon. Maybe we only care about notifying urgently those users that are in time zones which are likely to still be working. So in this case, Latin American users and North American users, we have 4,800. And we can then see if we look at that 4,802, and then we can see if we look at that, 40,795 are in sales, and we have 7 in marketing. So we've limited down the set of people we notify. But what we went here and said is, hey, the sysadmins, the network admins said we're doing maintenance on a switch. We can, as a system, immediately figure out who's going to be most likely to be impacted by that based off of what applications that they use or administer, and notify those users without playing that telephone game. So it's just a real much faster way and more accurate way to inform your users about the upcoming outage. And also maybe to discover that you're doing maintenance on a system that you really shouldn't be doing maintenance on at that time, and you should reschedule it because of the number of people that are going to be affected. So that's dependency analysis. And one of the other common scenarios is root cause analysis. And it is a common scenario because what root cause analysis allows us to do is to say, we have at our help desk a bunch of different people reporting tickets about things that are going wrong. And in this case, they're reporting tickets about the CRM and the Tableau instances and Oracle financials. And what we could do as a result of that is we could notify the admins of each of those services, and the admins of each of those services would then say, oh, is this a hardware problem? Is this a network problem? And then page more people. And we could end up paging, half of the IT staff of our company. But if we have a root cause analysis system in effect, what we can do is say, you know what? We know in our network that there is only one thing that is a common dependency among all the applications that are being reported being down right now, and that is this particular fiber switch. And I just double-clicked on that fiber switch, and we can see that there's other things that depend on it. But this is the common dependency amongst all of these applications that are being reported as having an outage. So what we can do is notify the owner of that fiber switch and say, hey, can you take a look at this, make sure that everything is up, or we can run some automated tests or manual tests before paging the entire or half of the entire IT group. We can limit the effect of this and get the problem resolved a lot faster. So that's just a quick example of Neo4j, the Neo4j browser, the Neo4j sandbox, some of the data sets that you can play around with today related to network and IT analysis, and some of the types of analyses that you might use in real life, dependency analysis, root cause analysis, once you have your network map inside Neo4j. So now we're going to hop back to the presentation here. And Jeff is going to go over the real-world telecom scenario, a couple of slides here, and then I'm going to go through a demo talking about what that might look like in Neo4j.
Yeah, I think that overview there that you just gave of the sandbox and the basic functionality, leads really well into this particular scenario. So in the context of a big communications provider, let's look at this idea around providing dynamic call routing capabilities. And some of the requirements that we happen to have here is, we want to, whenever there's a particular call being made, we know that there's a number of activities that need to take place. One is, the call needs to be routed according to its, path of least resistance, its lowest cost. We know that there may be other dependencies upon that based on what subscription services the caller happens to be subscribing to, or the recipient happens to be subscribing to. And then there's also factoring in the overall load on the environment. At any given time and any given day, what's happening embedding is also going to affect how we make decisions about how the call itself is delivered. So it's really requiring that dynamic balance for each and every single call. Oh, and by the way, it has to be really fast. Right?
Absolutely.
We're talking
Always have to be fast here.
less than 100 milliseconds, because which is really all of these decisions need to be made while the call is getting put through, and it's that time delay, that lapse between when you hit let's say send on your cell phone and before you hear the first ring, which is kind of the acknowledgement that the call has at least been delivered to the recipient.
But fast is what we do here at Neo4j, right, Jeff?
Yeah, exactly. Fast is what we do here, but God, this whole exercise is complicated, right? It's you've got locations about where people are, perhaps they're roaming. What about the overall cost of transport? What agreements does one telco provider have with another one? There could be tariffs involved. There could be fees according to times of day. This is getting ridiculous, Ryan. There's priority traffic, right? What about somebody trying to call 911 and they and get an ambulance delivered? That's got to take priority over you and I trying to do video chat over our phones. And then, like we just said, there's capacity routing activities, right? Making sure that load allocation is happening appropriately, making sure that we know what the quality of service levels are, because that might be part of the overall provider's subscription contract with either their subcontractors or their service providers or their product providers, etc. That's a lot of stuff.
A lot of stuff.
So how are we really going to do that if we end up trying to model all of this activity in a graph inside of Neo4j? You can see very quickly we can take into account, right, the transport costs. We can take into account how that relates to special services. We can take into account how that relates to alternate carriers during time of day. What's the fee structure that we're supposed to be providing? Whether or not the cops get priority, whether or not there's core load balancing activities happening. What's the risk mitigation activities so that the key government services get delivered quickly. What quality indicators, what metrics are we using to actually track all of that? That fits really cleanly in a graph, right? So you get, ideally you get, more intelligent routing capabilities, so the quality of service levels stay high. You can overall lower your CapEx requirements and perhaps, plan more effectively when you're going to take down a switch or when you're going to, upgrade a cell tower. Those kind of activities can really both, affect your quality of service to customers as well as your own costs of operation. And then there's the overall potential to reduce latency with with routing, making routing decisions based on how close are they to one router versus another, and is that router available? So these kind of activities are really, really great in terms of putting that into a graph, giving you better visibility into creating what-if scenarios, into coming up with predictive models so that you could actually figure out how customers might behave in a particular situation, and then optimize for that. So look for opportunities to renegotiate contracts, look for opportunities to build new cool services that you might not have thought of, and then work in additional pieces of information, because what's great about a graph is that as you add information to the graph, right, and create new connections, almost according to Metcalfe's law of the network, right, you're creating a richer, more valuable graph as you go along. And you really can't say that when you are throwing new information into a data lake, whether you're increasing the value of the data lake just because it's holding more stuff. That's not necessarily the case, but with a graph, it really is, right? Every connection increases the value of the entire model and the entire graph ecosystem. So it's a really cool kind of aspect about that activity. So I've laid out the problem for you, Ryan, but really, now
let me lay out the solution.
Now
for
tell
you,
me, how the heck are we going to fix this and solve this with a graph? So show me what a query, a call routing query and activity is going to look like.
Yeah, sure, Jeff. So basically, I mean, as we talked about, a network is a graph, and so your underlying telecom network might look something like this. And we have a caller on the left here, say in Vancouver, and then the on the right here at the top, say, is in Sweden, our lovely home country for Neo4j, and you're trying to route a call between those two devices. And you have all of these different options that you can take to do that route through a variety of different routers and switches here. You know, I'm only showing a small subset here for demonstration purposes. I'm sure all of you know that this is actually much more detailed here. But we have all of these different options for our routes. And the question that we have to ask ourselves is, what actual route are we going to take? So if we zoom in here a little bit, I've added some properties on these relationships. So if we can think about each of these routes that transit between these different routers, we have a property on that related to the cost. Now I've made it simple here and just had a flat cost per minute for making those connections. But in reality, this is based off of time of day and capacity and things like that. So we can have some more complicated properties on those relationships as well. But then we also have features. So when someone makes a call, do we need to route it over a connection that has the ringback feature available, or custom ringtones, or something like that? And then I've also indicated, you could have some additional properties, such as what is the current packet loss on that connection. And that would determine the quality, obviously, especially, a VoIP call would determine the quality of that connection. So we have a variety of different properties on our relationships. We have a graph of our nodes and our relationships. And then we would use that cipher query language that we talked about earlier to basically say, hey, I have switch A and switch Z. I'm trying to go from A to Z. Use a graph algorithm, in this case, the Dijkstra algorithm, with a weight assigned to it. So I want to go from A to Z over all of the route relationships. I am going to put a restriction on that. And for those of you who are familiar with this Dijkstra algorithm, I added that feature here on the slide here in terms of restricting the traversals, but that's a very common thing that people do in Neo4j. So we're restricting to say, has ringback true, capacity remaining is greater than 0.05, and a packet loss less than 0.0003. And then I am looking at the cost relationship and using that as my weight. And I could certainly make this more complicated as well, but in this case, I'm just saying that the raw dollar cost, find me the shortest path between those two switches with the smallest real dollar cost, where those features are met, and it's within capacity, within our packet loss ranges that we're comfortable with. And this is a graph query, folks. Like, this is very much a graph query, and that's why I think it's really important to represent this data in a graph as opposed to the set of Bessie tables that Jeff showed you earlier, where this is traditionally represented, because this allows us to take advantage of the properties of a native graph database, where you have index-free adjacency, and you can traverse this graph super efficiently to make that decision in that 100 millisecond time period. So after we run this query, we basically get the results, which is a set of routes, or one route in this case, but it could be a set of routes that are used for redundancy and passed on to our routing system to make that decision about what the final route should be. But we know in this case the purple highlighted route is our least cost route between those two switches that serve those callers, and we know that route supports the feature that we're looking for and has the amount of packet loss that we're comfortable with, and has the capacity that we need to make our call. And all of that you can do super fast in that under 100 millisecond time period, and route your calls more efficiently. With more properties, I should say, with a lot more data going into those decisions.
Yeah, very, very, very cool. So let's look at what it takes to actually build customer-facing products with Neo4j. And as we do that, we're going to look and consider incorporating things like your CMDB, your assets database, network monitoring data. You can take application monitoring data, additional business process information, stick that into the into Neo4j, into a graph-based system, and imagine both taking analytic snapshots for analytic purposes, taking and adding in your own, whether it's your own application engines, your own algorithms that can do that kind of cost analysis that Ryan just walked us through. You could do other impact analysis type capabilities. You could create your own extensive rules engine based on whatever quality of service features that you're trying to offer, or either the customers or the network management environment itself. You can do CEP activities that might identify where an application is failing, or where there's suspicious activity happening. You could maybe take on other additional services. So the overall sets of use cases there's an immense number of them. Whether it's traffic management, configuration management of how the network topology is supposed to be configured at any given moment. There's entitlement management, what customers are allowed to use and not. There's overall customer experience information that you could model as a graph. There's SLA, trouble tickets, fault management. Like whoever thought that there would happen to be both an earthquake and a hurricane hitting Reston, Virginia in the same year, right? But it really happened. And the network environments in and around Reston, including one of Amazon's environments, et cetera, we're all affected by both of those natural occurrences. There's quality of service capabilities you could do here. There's cost analysis capabilities here. So the opportunity for creating high value products around these kind of use cases is really extraordinary. And a way in which to differentiate your overall solution, the activities and the things that the graph actually provides you. Enhance your products to integrate new and unusual sources and model those as relationships, so that you're actually creating expanding value in the graph that you build. Create new and hidden patterns. Identify those much more easily to craft a new market opportunity. The beauty of the graph is it iterates really rapidly because typically changes don't affect what exists in the graph at any given time. So evolving the graph is very, very natural, and something that developers really, really enjoy about it. And then there's ultimately creating high degrees of performance at scale as the environment's building. So with us and working with Neo4j, the activities, you prototype very quickly, you can develop proofs of concept very easily, to streamline your overall execution of your product, and we can give you expertise at scale because of the thriving network of and community built around Neo4j that we can help marshal resources who are indeed experts in your field and can help you with your kinds of graphs. So a very, very active community that builds out very, very easily. So overall, in terms of the telco industry itself, 8 of the top 10 software vendors are already using Neo4j. 2/3 of the largest telcos are already using Neo4j, including Orange, including Telia, including Telnor, and of course we have more than 500 vendors are building products around Neo4j. So whether it's things that Cisco is doing. They tried the relational route but found that it was lacking. It wasn't responsive enough. Or other vendors like Pitney Bowes is using Graph as a vehicle for delivering their master data management, their data governance, and their fraud detection capabilities. So really great kind of examples of vendors building significant products on top of the Graph. So as we leave you here, the thing we want you to remember is the ecosystem itself matters a lot. Graphs are very easy to understand, as we continue to talk about, but they still require degrees of expertise and practice, and the application of the 10,000 hours you need to master a system. And if you really break that down, 10,000 hours is about 3 to 5 years worth of dedicated operational work on the activity that the ecosystem around Neo4j can actually help accelerate you to getting there much more quickly. We like to say around here that Neo4j is your fastest path to graph success. So finally, where we'll stop here today is we want to make sure you know that we have a huge amount of resources. It's growing all the time in terms of how to work with us. We have resources both in our operational environment for OEMs. We have resources in marketing to help OEM and partners develop what their offers are going to be and how to bring those to market. And we really want organizations like yourselves to become part of the Neo4j infrastructure. And I guess one last note here before we close out. I really want to thank Ryan Boyd here from Developer Relations for going through the examples that we just ran through. Amy Hodler in Product Marketing and Partner Marketing for helping with this event, as well as Alessandro. We really appreciate it. And so thanks again, folks.